So to start it off, let's ask the question, why do we even bother to sequence DNA? And the answer is simply because DNA matters. So DNA is a code of life that is present in every living cell. And it defines the structure of our bodies, and it also defines the way our organisms are functioning. So if we were able to develop a method of fast, cheap, and efficient sequencing of DNA, we will be able to correlate the particular differences in DNA sequence with the risk of occurrence of some illnesses like cancer. So we would be able to develop a method of personalized medical diagnostics and predictive medicine. It would allow us to shift the focus of the medicine from treatment of the ill patients to actual prevention of the illness before it occurs. So it is supposed to be faster and cheaper method of dealing with the health issues. Another possible application of DNA sequencing is for data storage. So data storage and replication is something that nature has been doing for millions of years. That's why it developed DNA as data storage protocol. And there are some ideas of using this kind of protocol for storing the data and replicating the data that we want to use. So for example, if you want to store your photos or videos or MP3s, you can do it actually in DNA molecule in a very effective way, so with very high density of information. So that's a kind of motivation. And now before we start to think how to sequence DNA, let's answer the question, or let's look closer at the structure of DNA. So for me, DNA is just a very large molecule that consists of these two large strands or molecular chains. If you look closer at the structure of DNA, you see that these two molecular backbones are connected by pairs of complementary molecules that come in 4 different flavors, A, T, C, and G. And the entire genetic information contained in the DNA code is encoded in this linear strand of these molecules. So we're just interested in learning the structure, the ordering of the molecules in the single strand. From the chemical point of view, these molecules look like that, so they are just small organic molecules that slightly vary in their structure and composition. So you may wonder why it is so difficult to sequence DNA. Well, there's a couple of issues to that. So the problem that we're looking at looks something like this line of code. So it's a long line of code built from 4 different building blocks, 4 different molecules. And we're looking at the very large molecules. So in human genome, we have around 3 billion molecules in this linear strand. It's really massive molecule. And in order to come up with any technologically viable method of sequencing DNA, we need reading rates on the order of millions of molecules per second. It's already challenging. And in order to make it even more difficult, we need single base resolution. It is because of the fact that even a single substitution in the DNA strand can have some health issues related to it. Can be correlated with the occurrence of some kind of cancer or other illness. So that's one of the issues. But also, another of the problems is the extremely low spacing between the consecutive molecules in the DNA strand, which is on the order of 0.3 nanometers. So that's why we need to apply methods of nanotechnology to deal with sequencing of DNA on the scale of single molecules. So nanotechnology is a field of science focused on investigation of physical phenomena and matter at the level of single atoms and single molecules. In my research, I am working on graphene tunnel junctions, graphene devices, for the purpose of biosensing. So at first, let me tell you a little bit more about graphene. It's relatively new development in the field of nanotechnology and solid-state physics, as it was discovered in 2004. And only 4 years later, 6 years later, the two scientists responsible for the discovery of graphene were awarded a Nobel Prize in Physics. So it emphasizes how big was the breakthrough introduced to nanotechnology and solid-state physics by the occurrence of graphene. So what is so unique about graphene is the fact that it's a truly two-dimensional material. It's ultimately thin, and it consists just of a single layer of carbon atoms arranged in this hexagonal honeycomb-like structure. Graphene can be easily extracted from graphite. Graphite, as we know it, for example, from pencils, is just a stack of multiple layers of graphene. And carbon atoms in the lattice of graphene are very strongly bonded. They interact by very strong carbon-carbon bonds. So it's difficult to break apart this plane of graphene. However, in the case of graphite, the interaction between the consecutive layers of graphene are very weak, and it's easy to break graphite into single-layer graphene. If you think how you can do it, it's quite simple. So if you just stick a Scotch tape to powdered graphite and you exfoliate it multiple times, there's a good chance that you'll end up with single-layer graphene. And that's exactly how you get your Nobel Prize. So nowadays we have also some more complex, sophisticated methods of fabricating graphene. You can try it at home. So for example, if you have a kitchen blender, you can mix the graphite powder, mix it with soap, water, shear mix, and you'll get your graphene. Obviously, in lab practice, we have slightly more complex methods of synthesizing graphene, but it's a different story. So let's say that we have our graphene sorted. That's an actual electron micrograph image of graphene with this hexagonal lattice. And what is the most important property of graphene for me is the fact that it's two-dimensional conductor. In fact, it's a very good conductor, even better than gold. So in my devices, I am applying graphene to fabricate electrodes. So I'm working with these graphene tunnel junctions. So you can see the diagram on the left. A typical device consists of insulating substrate, gold contact pads, and at the heart of the device, there's graphene tunnel junction, or graphene ribbon, with a tiny constriction in the middle. And my task is to introduce a very small gap in the middle, right here, separating the left electrode from the right one. This gap has to be small enough to accommodate just a single molecule or a single DNA strand. So in order to introduce this gap to graphene, I apply protocol of electroburning, which might be compared to the mechanism of light emission in incandescent light bulb. In such light bulb, you have a thin tungsten wire for which we are passing electric current, which causes the wire to warm up, to heat up, and it emits light. And I apply the same protocol to graphene tunnel junctions. So I start off with a thin 200 nanometers wide graphene constriction, and I am passing current through this device, which flows around in this loop. The current is causing the graphene constriction to heat up, and the local temperatures in this region can reach up to 1000 Celsius degrees, which is enough to start breaking carbon-carbon bonds and release carbon atoms, making the constriction narrower and narrower. And if you continue the process for long enough, there's a good chance of fabricating this nanometric gap between two graphene electrodes. And here actually the cool science begins, because if you keep on applying voltage to this device, you actually see that current is flowing through the gap. So current is flowing through vacuum or through air, which is really contrary to our everyday experience. If you look, for example, at these power lines, you have no current flow between two of them. However, at the scale of nanometers, different physical rules apply, and we have to treat electrons using quantum mechanics rules. So electrons are described as quantum mechanical waves that can penetrate through a potential barrier that corresponds to the gap between two graphene electrodes. And what is very important from the practical point of view is the fact that this tunneling current is very sensitive to everything that sits in the middle of the junction. So in the classical field of single molecule electronics, People are looking at the features of tunneling current modulated by the presence or absence of a molecule in the gap. So these molecules are firmly fixed. You can attach your molecule to the gap, for example, by equipping it with side anchoring groups that can stick to the surface of graphene, or by inducing a strong covalent bond by means of chemical reaction. So these systems are fully stationary. However, in my case, in the case of my research, I am looking at dynamic systems. So what happens here, the graphene tunnel junction is surrounded by a volume of water. Everything is covered in water. And I'm looking at the properties of current versus time traces as I apply constant voltage to these devices. In pure water environment, there's not too much happening. So you just see this low amplitude fluctuations in the baseline current. And then, at the next step of the experiment, I introduce to this water solution as low concentration of molecules like nucleobases A, T, C, or G, which are allowed to move freely in this water environment. They just diffuse around. And there's a good chance that one of them gets close enough to the graphene tunnel junction, and it starts to interact with the junction. So you can think about it as current flowing directly through the molecule. So that's why I can observe these discrete current peaks with high amplitude. And looking at the statistical properties of these peaks, I am able to distinguish between water solutions containing different nucleotides. So that's a proof of principle that graphene tunnel current can be used to distinguish between different molecules, different nucleotides. However, it's not full sequencing yet. And in order to realize the idea of DNA sequencing, we need to translocate, to drag a DNA strand through the graphene tunnel junction in a linear way. So in order to do it, we need a slightly more complicated method of fabricating devices, more complex device architecture. So devices for full DNA sequencing consist of a nanometrically thin suspended membrane with a nanopore in the middle. And the idea is to drag a DNA strand through this junction and read the sequence by means of tunneling current that is applied by two graphene electrodes aligned with the nanopore. So here's an actual electron micrograph of a device with a nanopore in the middle through which we'll translocate DNA strand and graphene constriction there. And there's a graphene tunnel junction in the middle. So the idea is that you apply constant voltage to this device and you look at the differences of current that are introduced by the presence of particular nucleotide in the junction at given time. And the big advantage of graphene applied to this method is its two-dimensional structure. It's ultimately low atomic thickness, which allows us to obtain very high resolution of reading, as opposed, for example, to gold electrodes, which even at nanoscale are still quite bulky and they're thicker than spacing between nucleotides. So this technology is still at the immature stage of development, and more work has to be done in order to turn it into a commercial product. But I hope that maybe in a couple of years, if you visit your GP, your DNA sequence will be sequenced in this way. Thank you for your attention.